Recall the definition of a set. A set was a collection of distinguishable objects, right? And that's all uh, required for a set. So each element is different from other elements, and but sometimes we want to classify a group of elements in a certain way. So probably some of the elements are, in a sense, similar to some other elements. So in this way, we may want to classify or group uh, some elements. And one way to do that is to introduce equivalence relations. Okay, here's a motivating example. Suppose we have a mapping from set A to set X. And we say elements A and B in the set A are related if f of A is equal to f of B. So this is just a convention we adopt here. So we have two sets A and X, and if two elements in the set A are mapped to the same element in X, then we agree to say that A and B are related. Okay, so in this case we write A is related to B. Okay. Now observe the following facts. First, for all elements in the set A, we have A is related to itself, right? And obviously we have this equality, so therefore A is related to A. This is trivial. And second, if A is related to B, then B is related to A. This should be obvious too. So first, if we assume this, if A is related to B, then this means by definition f of A is equal to f of B. And this implies f of B is equal to f of A, of course. Therefore, B is related to A. This is also trivial, almost. And third, if A is related to B and B is related to C, then A is related to C. This is also easily proved. Since A is related to B, then therefore f of A is equal to f of B. Given that B is related to C, f of B is equal to f of C. Therefore, this f of B is the same thing. Therefore, f of A is equal to f of C. Therefore, A is related to C. Okay. So actually this is an example of equivalence relation. Here's the definition. Let's say A is a set. It can be any set. Then we introduce a binary operator this is a tilde. This is just a symbol. You can use any other symbols to represent a binary operator. Binary operator means something that relates two elements of a set. So if this operator satisfies the following three conditions, we say this operator is an equivalence relation. Okay. First is called reflexivity. That is, for all elements in A, we have A is related to A itself. And second, it's symmetry. That is, if for all elements A and B in A related to B implies B related to A. In 3, it's called transitivity. For all elements of A, B, C in A related to B and B related to C implies A related to C. So if this binary operator satisfies all these three conditions, we say this is an equivalence relation. So the previous example we have seen is an example of an equivalence relation. So if we define this relation by this, then this is an equivalence relation. Let's see a few more examples. Let's see. For example, let us define a function f from integers to the set of two numbers, 0 and 1. And we define this mapping as this. F of n is equal to 0 if n is even, and equal to 1 if n is odd. Then we define an equivalence relation, this, if f of a is equal to f of b. And of course, a and b are integers. Okay. So as you can see, in this case, we use this three lines to represent this equivalence relation. I mean, we have to show that this is indeed an equivalence relation. And as we have seen in the first example, if we define, for some function, if we define a relation like this, then this is indeed an equivalence relation. Actually, this function can be considered as the remainder if divided by 0. Divided by 2. So if you divide an integer by 2, the remainder will be 0 if that number is even, or the remainder will be 1 if that number is odd. Another example is actually a counter example. Let's define a relation on the set of integers again. But in this case, we define A related to B if 2 divides A minus B or 3 divides A minus B. Okay, so you should show that this relation is not an equivalence relation. So among the three conditions, at least one of them does not hold in this case. So this is an exercise. we will see that equivalence relations are very convenient for classifying elements of a set. So related to that, let us define the notion of the equivalence class. Here's the definition. Let's say S is a set, and this tilde is an equivalence relation. On S. It can be any kind of equivalence relation. Then let A be some element of S. Then we define SA as this set. This is a subset of S such that X is equivalent to A. Okay, so this is a subset of all elements that are equivalent to A, and this is called the equivalence class of A. Equivalence class determined by A or containing A. Or containing A. Now we have the following theorem. So this justifies the usefulness of equivalence classes, equivalence relations, when we want to classify elements of a set. Okay, let S be any set, and suppose we have some equivalence relation, and let SA and SB be equivalence classes. Containing A and B respectively. Then we have the following results. First, if we take the union of all equivalence classes, then we have the set S itself. Okay, so this A runs over every element in S. So for each element in S, we can define an equivalence class, SA. So we change this A one by one and take the union of all equivalence classes. Then that union becomes the set S itself. And second, SA is equal to SB if and only if A is equivalent to B. Okay, and three, either SA equal to SB or SA cap SB is empty for any A and B. Okay, so this means, for example, either SA and SB are identical or they have no common elements. Okay, so there are no such cases as this. So, for example, SA is included in SB, or they have overlap, but So they have some overlap, but these extra elements are not present. So this cannot happen. This cannot happen. Either they are equal entirely or they are different entirely. Now let's prove this. First, prove this one. Clearly, SA, the equivalence class containing A, is a subset of S. I mean, by definition of the equivalence class, it's a subset of S. So therefore, if we take all the union of all equivalence classes, since every this subset is a subset of S, so this union is still included in S. And for all element A of S, we have A is an element of the equivalence class containing A by definition. So this means for every element of S, there is some equivalence class that contains that element. Okay, so this means A is of course included in the union. Let's call it A prime here to avoid confusion. So since this is included in SA, A is also an element of this union. So this means S is a subset of this union. So since we have this and we have this opposite inclusion, so therefore these two sets are equal. Okay, so that's done. And the second part, suppose SA is equal to SB. Wait a minute. What we are going to show is this one. So if we assume this, then we can derive this, and if we assume this, we can derive this. So that's what we are going to show. So first, suppose these two equivalence classes are identical. Then this means by definition, A is an element of SA, but since SA is equal to SB, therefore A is an element of SB. So this means A is equivalent to B, because SB is the set of all elements that are equivalent to B. So since A is such an element, so we have this. Now, conversely, suppose A is equivalent to B. Then if X is an element of SA, then X is equivalent to A, no, by definition. But A is equivalent to B. So by transitivity, of the equivalence relation, we have X is equivalent to B. Therefore, X is an element of SB. Okay, and we can go in the reverse direction. First, if we assume this, then we have this, but transitivity says x is equivalent to a, but uh, equivalent to a. So this means x is an element of SA. Therefore, okay, so from this argument, we can say SA is a subset of SB. By the reverse argument, we can also say that SB is a subset of SA. Therefore, SA is equal to SB. Okay. Now, three part. So part 3 says it is either two equivalence classes are identical or they have no common elements. So uh, suppose SA cap SB is not empty. So if this is not empty, then we can pick an element C from this intersection, right? So this means C is an element of SA and C is also an element of SB, right? So this means C is equivalent to A and C is equivalent to B. Therefore, by transitivity and symmetry, A is equivalent to B. And from this, in the second part, we have shown that this is equivalent to SA equal to SB. Okay, so this means if there is any common element, then the two equivalence classes must be identical. So if it doesn't, so if this is not the case, conversely, by contrapositive, if this is not the case, then the intersection should be empty. So we are done. What's nice about this theorem is that it says if we have an equivalence relation, based on that relation we can partition a set into disjoint parts, disjoint subsets. Okay. So we can split the set into some subsets which are non-overlapping, but together they cover the entire set, something like this. So let's give a name to this situation. Here's the definition. Of partition. Okay, let's say we have a collection of subsets. Okay, this is like a set of sets, a collection of subsets of S. So these subsets are indexed by this index lambda. So we have something like S1, S2, and so on, maybe Sn or something. It can be uncountable. It can be infinite or finite. So suppose this is such a collection, and if these two conditions are met, we say this collection of subsets is a partition of S. Okay, first, S lambda and S mu. So two elements of this collection is empty. Okay, so this intersection is empty if uh, lambda is not equal to mu. Okay, so for two different elements of this collection, they have no common elements. And if we take the union of all elements in this collection, this is equal to the set S. So this one we say mutually disjoint. And this property we say collectively exhaustive. Meaning together these subsets cover the entire S. So it's exhaustive. So if these two conditions are met, we say this collection is a partition. Of S. Okay, so this means this collection of equivalence classes of collection of all equivalence classes of a set S makes a partition of S. So as we have seen, it's either this or this. Either, not neither. It's both this and this. Okay. In this case, if we have this this scenario, then we just identify this set as this set. So we don't distinguish them. Okay, since they are equal as a collection or a set of sets, a set of subsets, then these two subsets are indistinguishable. So they are the same elements in this collection. So if they are different, they have no common elements, so they are mutually disjoint. So in this way, by introducing an equivalence class, we can classify the elements of a set based on the criteria that defines that equivalence relation.